And our moment at point C towards D is what? Minus 49.06 kilonewton meter. And our moment at point D towards C is what? Minus 24 point what? 5.3. However, it is possible for you to have what I have here. It is possible for you to have positive here, negative here, positive here, negative here, positive here, and positive here. However, it's either you have it in that form or you have it in this form. What it means is that if you are considering your moments, if you are saying let summation of moments about this direction, let it be equal to 0, you might have this. However, if you say let summation of moments in this direction to be equal to 0, then we have the reverse case. I hope you understand me. So it is possible for you to be arriving at plus 39, while another person is arriving at minus 39.17. It is not that you are wrong, no. The only thing is that your sign convention that you use is different from what the other person is using. So please try and master the way this mechanism work. That is why I always tell you that if you are starting with this sign convention, make sure that is what you adopt till the end of the calculation. Because if you use something otherwise, you arrive at a wrong answer. Now, in our calculation, we said these are the moments at the joint, right? Now, however, this is not the final area that we're going to. There are still some things that we still need to get. This is the members end moment. We need to calculate the members end shears. When I say members end shears, that is the forces at each point that you are considering. So how do I calculate that? If we recall, I think the diagram that we had was something like this. This is point B, right? Point A here, and I said this one is 1.5 kilonewton per meter, right? And this distance is 20 meters, right? And the other distance, it was loaded at the center here, and this is point C here. Let's say I have another point here, and this distance is what? 20. We have from here to here to be 10, right? And this other one, from C to D, it is not having any load, and the span is what? 15 meters. Very good. Now, what we have arrived at is that in this diagram, we have said if we segment this beam, this continuous beam, that is making it, we are splitting it. What we're trying to say is that this beam, we have a kind of moment like this in this form. That's this one. If I have it like this, then this one will come like this. Now, what I'm trying to say is that if this is minus 39.15, this will be equal to 71.7. However, for the second area where we have this point blue, what I'm trying to say is that if we apply a moment like this and like this one will now be minus 71.7, while this one will be 49.06. Likewise, the last one where we feel there's no loading, we will still have the same thing like this. The moment will still be applicable. However, we have minus 49.06 here, and at this side we have minus 24. So when I say minus 24, that means this one, that one too will go in this direction. Minus 24.53. Why is it so? Because there's no loading here, so the same moment we try and make it to rotate. That's why you can see it as if this one is different from what we have in the other scenario. What I'm trying to say is that if I have this particular shock, if I have this shock as a beam, when it's loaded here, what happens at the end? Let's say I'm holding it like this. If I punch this piece down, it want to move in this direction. So this, as it's trying to bend in this direction, the support will try to counter the force and then putting another moment to resist the loading that is coming. So this is the function of this moment we have here. Now, we have talked about the members end moment. We want to look at the members end shears now. How do we go about that? It is very simple. Let us take this first case as a scenario. We already know that, okay, this is 39.15 here, and let's say our sign convention that we use, I don't know the sign convention that we use, I think we use, is it this one we use? I don't know. I think this is what we use. Something a moment about, now, I want to show you something. Please, watch what I'm showing you here. It is very important for you. Because this is where many of us will miss the calculation. I want to treat this one now. I want to get the end shear here and the shear at this particular point. How do I go about it? I'm taking this one as an example. I'm considering this one alone. Looking at this one, you know we have how many moments? We have 2 moments here. We are saying that from what I have here, let's say that the one that is moving like this is a negative. So this one is positive. That's what it is. Right? Now, I want to look at what will be the shear in this particular point. If I want to calculate the shear, let me say my reaction at point A. That's the term that you people understand very well. Let's say I want to get my reaction at point A, and likewise there is another reaction at point B. How do we go about it? If I want to get reaction at this place, we take moment to this point. Right? So if I take moment to this place, if I take moment to this point B, who can tell me what equation I will have? Let me say summation of moments about point B to be equal to 0. So what will I have? Can somebody tell me what I will have? Okay, you're not seeing it. Let me be writing it. Okay, I think I will have to erase the diagram. Sorry. Okay, can you see this place? If you cannot see it, maybe you move to this side. Just move to this side. Because we are trying to get the recording for the people that are not in class. Those that cannot see it, just move to this side a little bit. Just make sure you are seeing it. I will try as much as possible to write, because for my screen, the places that are clear, this place is clear up to somewhere around here. It's very clear. So that's why I'm trying to avoid this side of the screen. So, as I was saying, we want to look at the members shear in this particular place. Now, to calculate the member shear here, what did I say we do? We take moments about point B. So if I want to take moments about point B, I said summation of moments about point B. We are saying it is equal to 0. So how will I write the equation? I have minus 39.15. That is the moment acting, right? Now, what is this span? 20 meters, right? However, if you look at this place, from this place, after this moment, there's a reaction RA that we have here. I will have to take that one into consideration. Because we are taking moment to this point. We have, since we said, let this one be positive. Now, how will this reaction at A, how will it get to B? Will it be positive or negative? No, please, I want you to look at it this way. Let's look at it this way. I'm standing like this. I'm standing like this. I want to add something. I want to add this thing, this particular object. I want to add it. I want to add this object. Because I'm standing like this. Or let me say I want to add this object. Let's say I want to add this object. Which direction will my head go to add this object? To go like this. Are you sure? Yes. Very good. The same thing applicable. Look at this particular shear force. It's pointing in this direction. It's coming to this place. How will it go and head that place? How will it go? What direction will it move? it will move like this. So that means it moves like this. So when it's moving like this, what does it mean? Is it positive or negative according to our science formation? Positive. So I will say plus RA times, because we are talking about moment. Moment is force times perpendicular distance. So what distance will it cross to get to B? Times 20. That one is for this reaction RA. You have done this already in your 200 your year 2. You should still remember, but I'm trying to come back to your level so that you understand. Now, let us now look at it this way. We are taking consideration of this reaction. However, that's not the only thing happening on this particular book. There's another UDL applicable here. How will I turn this UDL to a point load and then apply it as a force times perpendicular distance to get a moment? How? Because it's a uniformly distributed load, the first thing I will do is I will multiply that one by the span first. Once I do that, let's say this is W. By the time you say WL, it turns this to a point load, right? And that point load will be acting at the centroid. You should know this thing. This is your basic elementary, what's it called? Basic elementary mathematics. Now, since we said this one is 1.5 kilonewton per meter, right? Now, if I want to turn it to point load, it will be 1.5 times 20. Then it will not be a point load acting at this point, right? So I don't know the sign it will be first. I don't know the sign I will put here. Let me just write it. 1.5 times 20, making it a point load acting at this centroid, right? A point load acting at this centroid. Now, this is just a force, and we're looking for moment. Moment is force times perpendicular distance, right? Now, this one is acting in this direction. What is the perpendicular distance? Distance from here to here? 10, right? Or times 20 over 2, right? Yes. That's the one you know. Which one do you prefer? 10. If I put 10, some of you don't know where that 10 is coming from. That's why I put it 20 over 2. Now, what will be the sign convention? Now, looking at it, this man is pointing in this direction. How will he get to this place? Which direction is he going to take? How will he go? Will he go like this? No. Like this? Yes. So if it is like this, what is it? Do you understand? Now, do you have any other shear force again? No. But we have a moment here. That moment, we have to add that moment. That moment is plus 71.7, right? Now, all these things, we said it is equal to 0. So from this now, what are we going to do? We are going to, can I get the duster? From this, what we are going to do is that we are going to make RA the subject of the formula. All this equation is very simple. If you are very fast, you can do the calculation for us. Okay, let me see right under it. Can you see this? Let's see this place. I will give you the video on our group platform. Now, from here, let me do this one. This times this will give us what? Let's say this is 10. That's 50 times 20. 50 times 20 is what? 30. Are you sure?
1.5 times 20 is 30.
That's 300. We have 300 here, right? We have 300 here. So now, I can say 20 times RA equals to 300 minus 71.7 plus 39.15 all divided by 20. You agree with me? From here, this is what we want to make the solve formula. If you carry this one to this side, it will be positive. If you carry this one to this side, it will be positive. If you carry this one to this side, it will be negative. You are not following me? From what I have here, minus 39.15 plus 20 RA. Let's hold this one at this side. Every other thing we're taking it to the other side. But this time around, sorry, this 20 is what I'm using to divide it here. Sorry. You understand now? Oh, you are? So what will be our array now? So our array, let me find calculator. Okay, so let's calculate our array now. That's 300 minus 71.7 plus 39.15 which will be 267.45. Now let's divide it by 20. What are we going to have? Divided by 20.
13.3.
So what it's saying is that our reaction at A is 13.3725. Very good. Kilo Newton. Now, we have gotten our reaction at A. What is our reaction at B? It is very easy to calculate the reaction at B. There are two methods of doing that. It's either I take moment to this point and do the same procedure, or I sum my summation of, or I use this one, summation of forces along y-axis to be equal to 0. Let me go to the easiest part. Let me sum my forces along y-axis to be equal to 0. So if I want to sum the forces along y-axis, mind you, this is forces, not moment. So how many forces do I have? I have RA, so I should say RA plus reaction at B should be equal to what other reaction do I have? Only this UDF. And this UDF, if I convert it to a point load, it's supposed to be WL, right? So which is WL is what? 1.5 times 20. That's 30. So my reaction at A plus reaction at B should give me 30 kilonewton. So I can say my reaction at B equals to 30 minus RB, right? Which is equals to 16 point maybe 63 blah 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 kilonewton. You understand that? You don't understand? Which one you don't understand yet? You understand how we got this WL? You know how we got this WL?
Yes.
This one times this span. That's the equivalent of the point load, which is 30. So if I sum this and this, that is the summation of your reaction should be equal to, let me say, the summation of your forces along the upward axis should be equal to the summation of forces coming downward. Now, if I have RA plus RB equals 30, and we already know our RA, just carrying this RA to this side, that is 30 minus RB. 30 minus RA. RB is 30 minus RA. That will give us this, because this is 16, this is 30.37. Which 16? This one. This 13, do you know where we got this one?
Yes.
If you put this 13 here, if you remove it from here, what will you have? Please, you have to double up to understand and move fast with us. Any question? Now, I think I can, now, since we have done for this, so we know that our reaction at A is what now? Reaction at A is 13.37. 37 kilonewton. Reaction at B is 16.63 kilonewton. Now we want to get reaction at the second reaction at, let's say the reaction at B to C. But we'll still have another reaction here, right? We want to do that now. The same way we treated the same way we treated this, we'll treat this one the same way. So what do we have for this particular scenario? We have just this point load here, right? We have a moment here, we have a moment here. Now, let's say I want to get the reaction at this place. To get the reaction at this place, I take moment to this point, right? The way you are looking, are you following me? I told you the other time, if you want to get this one, we'll take moment to this point. So that we'll have this point that we are looking for, we'll be able to multiply with that distance to convert to a moment. Now, if I want to get moments for this particular one, if I want to get reaction for this place, I take moment to this point. And we already know that this is minus 71.7, this is 49.06 here. What I'm trying to do is that I want to say, let my summation of moment about point C, let it be equal to 0. And we are using what sign convention? That this is positive, right? Now, from what I have here, I have minus, let me say reaction bx. Let me use that bx. Let me say we're looking for reaction bx and reaction cx. Let's say those are the reactions we're looking for. Why am I using another thing? Because we already have something that we have labeled RB. That's why I'm not putting RB here. That's why I'm trying to differentiate with something like bx. Very good. Now, so we are summing this moment to be equal to 0. Now, what do I have here? I have a moment of minus 71.7. Well, then we have the reaction RBS. RBS times, what's the distance? 20. How will it go? How will it move towards that point? It will move like this, right? It will move like this. So, is that positive or negative? Positive. So I put a positive here. You understand? This your marker is running out of our. I think I have one. Let me see whether this. I should have changed this one. Okay. And now, do we have another reaction? The only reaction we have is this particular one here, which is 30 kilonewton, right? Yes. Now, this one, toward this point, how is it going to move? How is it going to move towards this point? This reaction at this point load. Yes. How will I take moment to this point with it? Negative. Like this, have it? Yes. That's negative, right? Yes. So I have minus, what's the value? 30 times, what distance is it covering? 30 times 10 now. The distance from here to here is what? 10. So that's the 10 we have here. What other thing do I have? I have a moment at this point. So the moment, is it positive or negative? Plus 49.06. Plus 49.06. Now, our RBX should be equal to something like, which should be equal to 0, right? So we take this one to this side. We have 71.7 plus 300 minus 49.06, all divided by 20. Do you know wherever that? You say? Very good. So we substituted this RDS, making RDS the center of the formula. So since we said all these equations, please, if you are writing to your notes, put this plus here because I don't have to time I'm putting it here. So this one is positive because it's moving to this side. This one will not be positive because it's moving to the other side, and this one will be negative because it's moving to the other side. Divided by that 20. So if you do the calculation, what are we going to have? That's 71.7 plus 300 minus 49.06. That's 322.64 all over 20. 16.132. Okay, so kilo Newton. Now that is what we are having at this point. We are having a point load of 16.132 here. We are having 16.132 here. Yeah, what were we having before? Let me write what we have here. I think this one is 16.63. This one is 13.37. Right? Very good. So we have 60.63 here, 60.132 here. So what are we going to have here? Let's summation of forces along y-axis to be equal to 0. So RBS plus RCS will be equal to what? We got to W, right? Which equal to 30 here. So I can put 30 here. So RCS will be equal to 30 minus RBS, which equals to 30 minus 16.132, which equals to 13.86 kilonewton. Right? So we have 30.86 kilonewton for this particular side, right? The same thing you did, we're going to now take this one into consideration this time around. We want to look at this one. We have gotten the shear force here, shear force here. That's the members end and shear force. We have gotten all of them, remaining for this and this. So how do I go about this? Now, for this particular one, let's call this maybe RCY, RCY, RDY. Now, let's say what we have here, we want to get moments to this particular point to get this reaction here, right? Can I erase this one? Can I erase this? Now, we want to obtain the reaction at CY and reaction at DY. How do we go about that? We take moments about D, summation of moments about D to be equal to 0. Don't forget our sign convention. We said this one is positive. That's what we have been using, right? Yes. So now, if you have said that, how will I write this equation? I have a moment here, which is, however, this is negative, so I have minus 49.06. That's the moment here. Now, this one to this point, will it be positive or negative? Positive. Plus RCY times what distance is it covering? 15. Now, do we have another reaction? But we have the moment here. What's the value of the moment here? Minus 24.53, right? Which is now equal to 0. Now, do you know how we got this? Any question on this equation we have here? Any question on that equation? Now, we want to make RCY the solid of formula. To do that, we just say, we take all these ones to the other side. So I have RCY times 15 to be equal to 49.06 plus 24.53, which is equal to so I have 49.06 plus 24.53. 73.5 73.53 sorry 59 59. So that's RCY times 20 and 15, right? So RCY will now be equal to 73.59 divided by 15, which is equal to what? 4.906. So the reaction here is 4.906, right? Now, the same thing we have been doing. Summation of moment and summation of forces along y axis to be equal to 0. Can I erase this? Now, let us look at the summation of forces along y to be equal to 0. So what will I have here? I will have something like RCY plus RDY to be equal to what? To be equal to what? To be equal to what? 15. Where is 15 coming from? Eh? Where is that coming from? We are dealing with this one. Do you have any shear force there? No. So this one will be equal to 0. Because there's no load coming like this. So what we're going to have is, since our RCY is 4.906, so we can say RDY equals to minus RCY, which equals to minus 4.906. So this side will be minus 4.906. That's the shear force at those places. Now, okay. Any question, please? Question? Question? Ask your question, please. Now, let me pause our recording. Do you know the advantage of all this reaction, all this movement that we're trying to do? Do you know the advantage or its purpose? You know, we may be asked to draw the shear force and the bending moment diagram. And at the same time, when we're designing a beam, we always use the maximum bending moment to allocate the number of reinforcement that we will provide. So what we are trying to do is that we are trying to look at the moment at each joint, so that you know what to provide, the number of reinforcement to provide at each support, whether you need to double the reinforcement. That is why when you see some design, at each support, at the support, they give you the amount of reinforcement. At the end, at the span, they give you at various interval for a continuous beam. I don't have a sample drawing here. Now, all those moments, those are what you cater for in your design. That whatever you are providing for should be able to cover for this particular moment that is acting. Now, I want to draw the shear force diagram based on what we have here. Let me see. Elema.
Yes, sir. 14. Okay, go.
Hello everybody. I am underway. This is 3,500 naira. I have 100 naira.
I will. Please, what will happen? This is what should happen. As far as this course is concerned, each of the students have a marker. Each of the students should have a marker. Are you getting me? I will be coming with my own marker too. You understand? But each student should have a marker. This course, before we finish a single calculation, we will exhaust the marker. Because I hardly dictate. It's more of calculation. And I want you people to understand that I'm coming down to your level, because that's the only help I can do for you. It won't make sense if I just rush it and I don't allow you to understand the principle. I hope you understand. Your own sacrifice should be getting markers so that you have something that is clear enough. You understand? He has tried, he went to get the marker for all of us in the class, but I don't want him to bear the cost alone. So we have to distribute the moment. We'll be getting to that in the next. You know what is paining me? This man is in school and he knows that he's having lecture and he's just coming by this time of the day. That's what is paining me. You are not doing me. The only thing I can do for you is that I will never give you extra mark. You understand? That's the only thing I can do for you. That's the only thing I can do for you. So, you know my principle. The people coming late after my calculation or towards the end of my calculation, they don't write their name. So here. So you know how you treat that case. And I wanted to draw the shear force and the bending moment diagram before you came. I was telling them that all this calculation that we got is for us to be able to draw our shear force diagram, so that we will know the moment and the shear at each point, so that we know what we will provide for when we are doing our design. Now, this particular kind of situation is not like a simple beam that you just draw and you just say just calculate it, maybe WL over 4, whatever it is, or you just say because we have UD here, it is WL square over 8. That particular one that you always use, general one, cannot work for this kind of situation. You understand? You will be over designing. That is why we are trying as much as possible to make sure we know what moment what shear is happening at each point. Now, I want to draw the shear force diagram. How do I go about it? I have a very lovely way that I love to treat my shear force diagram. I don't know whether it's right, I don't know whether it's wrong, but that's the principle I've been using since I started doing theory of structure. Now, what do I do? When I want to draw a shear force diagram, after putting the diagram here, I draw a straight line. I draw a straight line like that. This is my own method. Now, what do I do? I look at it. How is it loaded? When I have a uniformly distributed load, we have a diagonal line for shear force. But when we have a point load, it will just be maybe a straight line up or coming downward. I hope you understand, depending on the value. Now, I want to draw the shear force for this diagram. When I want to draw shear force, I won't be considering all these moments. I will only be taking those pointing upward or pointing downward arrow, right? Now, for this particular case, we have 1.5 kilonewton per meter here. So this is a UDA, right? Please, I think this. Okay, yeah. Let me use our new marker. Now, starting from here, what's the reaction at K? 13.3. I move from this point 0 here. I travel to 13.37. However, at point B here, it is 16.63. Because this is a uniformly distributed load, it slants. This 16.63 here. Sorry, I didn't record. So, as I was saying, let me to record this.
Yes.
Are you sure?
Yes.
Okay. So, as I was saying the other time, I said the way I draw shear force diagram, I draw a straight line. I want to draw a straight line to be equivalent to the span of what I want to draw the shear force diagram of. Then I start taking those shear force one after the other. Now, and I told you that if we have a uniformly distributed load, the shear force will be diagonal, slanting. But if we have a point load, it will either going up or going downward, as we have here. Now, for this particular case, we have 30.37 going up. Now, normally, if there is no load, it will continue to move at that side. But because it's a uniformly distributed load, it has to slant. Now, at point B, we already have something like 16.63, right? So it has to slant and go and meet that 16.63 like this, right? It slants like this, then come to this place. Now, after slanting, it covers this 16.63 to get to this point here. Now, at this 16.63, there's something I want us to look at. At point BX, it travels 16.132. So we have to travel 16.132. 16.132 to this side. Now, this 16.132, I continue to move straight until I get to this point load. That point load is what? 30 kilonewton, right?
Yes.
So I have to drop 30 kilonewton downward here. If I move 30 from here, what do I have? 13 point, I should have 30.86. So that means it is already in 30.86 here, right? So I continue to move in that direction till I get to this point here. 13.86, right? Then I move up. Right? Now, however, for this particular one, it's 4.906. I travel from here, 4.906 here. Is there any force here? No, I continue to move till I get to the end here, when we have minus 4.906, so I complete it here. This is the shear force diagram for what we have. Any question on this? You said? I should re-explain again. Okay. You already know the principle. As I told you the other time, when we have a UDL, we have it slanting diagonally. While we have maybe a point load or a downward arrow, it just comes in this way. Now, for this particular case, at this point, we have 30.37, which will move upward. However, we're supposed to be moving in this direction till we have a point load. Because this is a uniform distributed load, it's already pushing it downward already. So that's why it is slanting to this particular point. Though we don't know where it will slash, where it will end. But because we know at this place is 60.63, we know that definitely that's where it's going to terminate. So we draw that one, we finish for this one here. Now we move to the second diagram here, which is from B to C. It travels from here to here. That's 60.132. This is 60.132. Now it continues to move at that 60.132, except there's a point load that will force it downward. And this is the only point load applicable here, which is this 30 kilonewton. So this 30 kilonewton is forcing it downward, and we have it up to this place. If you continue to move at that particular stage, or except we see another force, but here we have another force here, 30.86 pushing it forward. So here we have 30.86 pushing it. We have 30.86 pushing it up there. This is what? What do we have here? 30. The whole of here is 30, right? Yes, very good. Now, for this particular place now, for this last one, we have 4.906. But that 4.906 continues to move, except we see a point load that will punch it downward. And there's no point load acting on this particular beam, except this one, which you have minus 4.906, which is going to force it to come and terminate at this point, starting point again. So I said this is our shear force diagram for this. Now, there's a saying that we have our maximum bending moment where our shear force is 0. Our maximum bending moment occurs at the point where our shear force is 0. Now, in this diagram here, where my shear force is 0 is at this point, right? This is where the shear force is 0. I also have it maybe around here. Let me see here. I have it around here, right? Okay, where are we touching the line? Let's say we have it here. Right? Those are the points we have. Let's see those are the points that we have, right? Now, for other cases, we already know what our moments are. At this place, we know what the moment is. At this place, we know what the moment is. At this place, we know what the moment is. At this place, we know what the moment is. But at this point, we don't know what their moments are. At this place, this one and this point, we don't know what the moment is, because that's like at the midspan. Ordinarily, in your normal elementary calculation, you will say WSK over 8, right? Which is what you have been doing. But for this case, it is not so. We have to calculate it. Now, how do we calculate it? It is very simple. I've started explaining for the many moments, but I will show you how we calculate it. Because I told you that we have the maximum bending moment at this point, we need to know that distance from each of those joints. What is the distance from here to here? We need to know those distance, right? I need to know the distance from this one. This one is very easy because it's I think it's 10 because it's at the midspan, so it's very easy. That one is very easy. But for this one, we need to know this distance. How will I know that? This is what I'm going to do. Let's say this is x. I try and draw something like a triangle. That's the method I always use. This is a triangle here, and this is another triangle here. I know this distance to be 20 meters, right? And I know this distance, this height here to be 16.63, right? Do you agree with me? Now, how will I know this distance? It's very easy. All I just need to say is, I have a distance at 13.37. I have the base to be x. At 30, I have the base to be 20, right? Do you agree with me? When I have the height of 30.37, I have the base to be s distance, which I don't know. When I have the base and the height to be 30, I have the base to be 20, right? So from here, I can calculate my s. What's my s? My s equals to 20 times 30.37 divided by 30. What will it give us? So 20 times 13 point.
8.91.
Okay. So 8.913. Yes. 8.913. So please, this distance is distance of 8.913 meter. At that point, that is where we are going to have our maximum bending moment. So now we want to draw the bending moment diagram. Can I erase this? No. Can I erase this main one?
Yes, sir.
Okay. Yes. Now let us look at it. It is very simple. Very simple. The method I always use, I will draw my straight line like this again. Like a very faint line. Now what do? I will just come to this place. What do I have in the first moment? The first bending moment at the joint, what do I have? We have minus 39.15. That's the first thing I have here. I draw this. I have that one here. Now, at this point, I have it at 71.7, right? Very good. At this point, I have it at what? 49.06. Now, at this place, I have it at what? 24.99. Minus 24.
Yes, minus 24.5.
Okay. How do I explain this one to you? Okay, let's start from here first. I have this moment here, right? Normally, when we want to draw a bending moment diagram for a uniformly distributed load, we have it as a parabola, right? When you want to draw, let's say this is your uniformly distributed load, right? When you have a uniformly distributed load like this, when you want to draw the moment, at times you can draw it like this. Have you? Another person can draw it like this. You are both doing the same thing. The only thing is that somebody is saying that is applying it at the, underneath, while another person is applying it on top. But the main thing is, what we're telling you is the value. Either it's negative or positive, it is the value that we're interested in, right? And for this case here, to have that uniformly distributed load, it's supposed to come like this. But I don't know where it will terminate. I know it's supposed to come like that. That's the normal rough diagram of a bending moment when you have a uniformly distributed load. But I don't know where it will terminate or where I will have my maximum point here. That is why I asked us to calculate this distance the other time. So this distance from here to here, that's your 8.913. Now, what is the value of the moment at that particular point? What is the value of the moment at that particular point? How will I know the value of the moment here? You say? It is very easy. Let's work it out. Let's say somebody is starting from here. You want to get the moment to this particular point. You say? We are not subtracting. We are doing full calculation. Full calculation in this one. We are doing full calculation. Let me show you the now. It is very easy. Don't panic. Just chill out. What are the things that I have? I have a uniformly distributed load here, right? Sorry. I have a moment here, right? I have a shear force here, right? I have a uniformly distributed load here. And I also have a moment at this point, right? But because I am taking moment to this point alone, it is very easy for me to do the calculation. All I need to do is, when we cut this one, at this point, bah! we put an ass, we strike it there. When we strike it with an ass, we forget about what is happening at that side. We are concerned about what is happening here. I hope you understand. Now, how do we go about the calculation? Please, once I make a cut at this point, you forget about what's happening at this side. We are considering from here alone to this side. Now, how do I take moment to this place? Because I have summation of moment towards point 8.99132 to equal to 0, whatever is equal to 0. So to do my calculation now, I start minus 39.15, then to this place. This R, is it plus or minus? Plus R A times, what's the distance? 8.913. That's the distance now.
Yes.
We are not taking moment to this place, we are taking moment to this particular point. And the distance from here is 8.913. Right?
Yes.
Now, do we have another force here again? Only this UDL. Now, this UDL is going to be, when we convert it to point, it comes like this, then to this side, so it's going to be negative, right? But how do I convert this UDL? It's still very easy. So W times X over 2, right?
Yes.
W times X will convert it to a point load, times X over 2 will convert it to a moment. So for this particular scenario, we have minus into the UDL is 1.5, right? Times the X is what? 8.913 times 8.913 over 2. Right? Or which equal to whatever we are looking for. Equal to whatever we are looking for. Equal to the moment at 8.913. Yeah. Now, this one, this array, we already know it's a 30 point. This is 30.337 now, right? I'm only putting array so that you understand what I'm trying to draw there. Now, let's do the calculation. This time, this is what? 30.37 times 8.913. 119.16.
166.
167. Let's do this at 7. This one is what? Times 8.913 times 59.581. Now, let us sum it. Let's see what we have. I have minus 39.15 plus 119.167 plus minus 59.581. 20.43. The value is 20.436. So what it's telling me that the value of the moment here is 20.436. Koye. Koye. You don't understand? Did you start the class with us? And you don't understand what I did now? Which area is it that you don't understand, if I may ask you? You said? You said everything?
No, I don't.
Record this. Okay. Now, the second scenario. The second scenario, which is this. I don't care about what is happening here again. I'm bothering about what is happening here. Now, for this particular case, we already know that it is at the center, which is 10 meters from here, right? So we want to take moments at this point. So we are putting our section or segment or section, we are sectioning this beam at this distance here. Now, the same thing we did in the first case. We want to get the moment, summation of, let's say, summation of moment towards the 10 distance, towards the 10 meters distance. Let's sum it to because so it will now be, give us what? The same thing we did is what we want to do for this particular case. However, at this place is minus 71.7. Then we continue to move. This point load. Yes, my Carol.
Yes, sir.
Okay, let me need 2 minutes.
All right.
So now, please be attentive so I round up this one. This first times perpendicular distance, it will give us because this one is positive, this is this is positive, right?